Look up at the night sky. Every point of light you see, every star burning across the cosmic dark, holds worlds in its grip. And for as long as humanity has gazed upward, we have imagined those worlds as perfect spheres. Smooth, symmetric, round like the earth beneath our feet, round like the moon that pulls our tides, round like every marble of rock and gas that spins through the void. This is not superstition. This is physics. Gravity does not tolerate imperfection. When enough mass gathers in one place, when billions upon billions of tons of rock and metal and gas collapse under their own weight, they have no choice but to form a sphere. It is the only shape that allows every particle to be as close as possible to the center. The only shape where gravity pulls equally in all directions. A sphere is not beautiful by accident. It is beautiful because it is inevitable. Or so we thought. 1,200 light-years from Earth, in a region of space so distant that the light reaching our telescopes tonight began its journey before Charlemagne crowned himself Holy Roman Emperor, there exists a world that should not be possible. A giant planet, larger than Jupiter, circling so close to its star that a year lasts barely 22 hours. A world where the temperature never drops below 2,500 degrees Celsius. Where winds scream across the surface at 5,000 kilometers per hour. Where the sky burns with perpetual radiation. But none of that is what makes this world impossible. What makes it impossible is its shape. This planet is not a sphere. It is a lemon. Stretched. Deformed. Pulled into an oval so extreme that its equator bulges outward while its poles sink inward, as if invisible hands have grabbed the world by its axis and squeezed. The distortion is not subtle. The difference between its widest point and its narrowest is more than 10% of its entire diameter. If Earth were deformed this way, the distance from the North Pole to the South Pole would be 400 kilometers shorter than the distance across the equator. Mountains would become chasms. Oceans would spill toward the bulge. The entire architecture of our world would collapse. And yet this planet endures. Spinning, burning, dying slowly in the light of its star. Its name is WASP-103b. And it is a message from the universe, written in gravitational mathematics, telling us that even the laws we consider absolute can be bent until they scream. The story of WASP-103b begins not with its discovery, but with a question humanity has asked for centuries. What shapes the worlds beyond our own? For most of history, we could only guess. We looked at our moon, perfectly round through even the crudest telescope. We looked at Jupiter and Saturn, spheres banded with clouds, their moons hanging in space like pearls on an invisible string. When we finally sent machines beyond Earth's atmosphere, when Voyager swept past Neptune and Cassini dove through Saturn's rings, the answer seemed clear. Planets are spheres because gravity demands it. But gravity is not the only force in the universe. In 2003, the European Space Agency launched COROT, a space telescope designed to hunt for planets around distant stars. Its method was simple, elegant, and devastatingly effective. It would stare at a single patch of sky for months, watching thousands of stars simultaneously, waiting for the telltale dimming that occurs when a planet passes in front of its host star. A transit. A shadow cast across light-years of space. Most transits look the same. The star's brightness drops by a fraction of a percent, holds steady for a few hours, then returns to normal. The depth of the dimming tells you the planet's size. The duration tells you its orbital period. Clean. Predictable. A sphere passing in front of a sphere. But in 2014, astronomers analyzing data from the WASP survey, the wide-angle search for planets, noticed something wrong with the transit of WASP-103b. The light curve, the graph showing how the star's brightness changed over time, was asymmetric. Not dramatically, but enough that the computers flagged it as anomalous. Enough that human eyes, trained to spot the subtle signatures of planetary architecture, saw something that should not exist. The planet was not round. At first, there was skepticism. Telescopes lie. Pixels malfunction. Atmospheric distortion can twist light into false patterns. But as more observations accumulated, as different telescopes in different parts of the world confirmed the signal, the truth became unavoidable. WASP 103b was deformed, stretched into an ellipsoid by forces so extreme they overwhelmed the planet's own gravity. The sphere, the shape we had assumed was mandatory for all worlds, had been broken. This was not the first time humanity discovered something impossible in space. In 1781, William Herschel found Uranus and doubled the known size of the solar system overnight. In 1930, Clyde Tombaugh found Pluto and proved that the outer darkness held more secrets than we imagined. In 1992, astronomers found the first exoplanet orbiting a pulsar, and we realized that planets could form in the radiation-soaked hell around a dead star's corpse. Each discovery rewrote the rules. Each one reminded us that the universe is not obligated to make sense. But WASP 103b was different. This was not a new type of planet. This was a violation of shape itself. A challenge to the geometry we thought was universal. And the question that echoed through every observatory, every university, every mind that heard the news was simple. How? To understand how a planet becomes a lemon, you must first understand what holds a planet together. Gravity is not gentle. It is a compressive force, a vice that squeezes matter inward with relentless patience. Every atom in a planet is pulled toward every other atom. The deeper you go, the greater the pressure. At Earth's core, iron is crushed with a force of 3.5 million atmospheres. At Jupiter's core, hydrogen is compressed so violently it becomes metallic, a substance that cannot exist anywhere on Earth's surface. This inward crush is what creates the sphere. If one side of the planet bulged outward, gravity would pull it back. If a mountain rose too high, gravity would flatten it. Over millions of years, over billions of rotations, gravity grinds away every irregularity until all that remains is the purest form, a sphere where every point on the surface is equidistant from the center. But gravity is not the only force acting on a planet. When a planet orbits close to a star, something else enters the equation. Tidal forces. The same force that lifts Earth's oceans twice a day as the moon passes overhead. The same force that has locked our moon so that it shows us only one face. The same force that tears comets apart when they venture too close to Jupiter. Tidal forces arise because gravity weakens with distance. The side of a planet facing a star feels slightly stronger gravity than the side facing away. This difference is tiny when the planet is far from the star. But when the planet is close, when it orbits in the realm where temperature and radiation make rock glow and metal vaporize, the difference becomes catastrophic. Imagine pulling on opposite ends of a rubber ball. At first, nothing happens. Then, as you pull harder, the ball begins to elongate. The sides stretch. The middle thins. If you pull hard enough, the ball tears apart. This is what tidal forces do to planets. They stretch them along the line connecting the planet to the star. The side facing the star bulges outward. The side facing away bulges outward. The poles, perpendicular to the tidal axis, sink inward. The planet becomes an ellipsoid. A lemon. For most planets, this deformation is negligible. Earth experiences tidal forces from both the Moon and the Sun, but they only raise the crust by a few centimeters. Jupiter's moon Io, the most volcanically active body in the solar system, is stretched by tides from Jupiter itself, but even Io maintains a roughly spherical shape because its internal structure is strong enough to resist. WASP 103b has no such luxury. WASP-103b orbits its star at a distance of just 0.01977 astronomical units. To put that in perspective, Mercury, the closest planet to our Sun, orbits at 39 cents. Earth orbits at 1 AU by definition. WASP-103b is 50 times closer to its star than Earth is to the Sun. It is so close that it completes an entire orbit in 22.2 hours. A year that lasts less than a day. At this distance, the tidal forces are not a gentle tug. They are a gravitational hurricane. The star's gravity does not merely pull on WASP-103b. It tries to rip it apart. Every second of every hour, the planet's outer layers are being stretched toward the star and away from it simultaneously. The atmosphere screams. The clouds boil. The entire world is locked in a battle between its own gravity, which tries to hold it together, and the star's gravity, which tries to tear it into a ring of debris. And for now, the planet's gravity is losing. The deformation of WASP-103b is quantified by something called the Love number, named after Augustus Edward Hough Love, a British mathematician who in 1909 derived the equations describing how elastic bodies deform under tidal stress. The Love number measures how much a planet's shape responds to tidal forces. A perfectly rigid body has a Love number of 0. It does not deform at all. A fluid body, like a water balloon, has a high Love number. It stretches easily. WASP-103b has a Love number higher than any planet in our solar system. Higher than Jupiter. Higher than Saturn. The measurement suggests that its interior is not solid but partially fluid, a churning mass of metallic hydrogen and helium, convecting violently under the dual assault of internal heat and external tidal stress. This fluidity allows the tidal bulge to grow to monstrous proportions. The planet's equatorial radius is estimated to be 10 to 15% larger than its polar radius. In absolute terms, that is a difference of nearly 20,000 kilometers. A deformation so large it can be detected from 1,200 light-years away by analyzing the precise timing of the planet's transits. But there is a threshold. A line in the mathematics beyond which no planet can survive. It is called the Roche limit, named after Édouard Roche, a French astronomer who in 1848 calculated the minimum distance at which a celestial body, held together only by its own gravity, can withstand the tidal forces of a larger body. Come closer than the Roche limit, and you do not merely deform. You disintegrate. For a fluid body orbiting a star like WASP-103's host, the Roche limit is approximately 2.5 times the star's radius. WASP-103b orbits at roughly 3.2 stellar radii. It is outside the Roche limit, but not by much, and it is getting closer. Every world you can see from Earth tells a story of motion. The Moon drifts away from us at 3.8 centimeters per year, carried by the same tidal forces it exerts on our oceans. Mars once had moons closer than Phobos, but they spiraled inward and shattered, leaving a ring of debris that eventually rained down onto the surface. The asteroid belt between Mars and Jupiter is a graveyard of worlds that never formed, torn apart by Jupiter's gravity before they could coalesce. Tidal forces do not merely deform. They transfer energy. When a planet is deformed by its star, it does not return to a perfect sphere between each orbit. The bulge takes time to form, time to relax. This creates friction inside the planet. Heat. And that heat is not free. It is stolen from the planet's orbital energy. WASP-103b is losing energy. With every orbit, the tidal flexing heats its interior, and that heat radiates into space, and the energy lost to radiation comes from the planet's motion. The orbit decays. The planet falls inward. The mathematics are precise. Based on observations of the planet's transit timing variations, Astronomers estimate that WASP-103b is spiraling toward its star at a rate of approximately 10 meters per year. That may sound slow. 10 meters is the length of a bus. But in astronomical terms, it is a death sentence. In 200 million years, WASP-103b will reach the Roche limit. The tidal forces will exceed the planet's gravitational binding energy. The outer layers will begin to strip away, peeling off like skin from a burn victim, forming a vast ring of gas and dust around the star. The core, if it is solid, may survive for a time, a naked remnant orbiting inside a nebula of its own former atmosphere. But eventually, even the core will be consumed. 200 million years. Long enough for dinosaurs to evolve, dominate, and go extinct. Long enough for continents to drift across an entire planet. Long enough that when WASP-103b finally dies, no human alive today will have any descendants left to witness it. But on cosmic timescales, 200 million years is nothing. WASP-103b is already in its final act. We are watching the last chapter of a planet's life, and the universe does not grant extensions. WASP-103b does not rotate freely. It cannot. Its proximity to the star has locked it into what astronomers call synchronous rotation, the same phenomenon that keeps our moon's far side forever hidden from Earth. One hemisphere of WASP-103b faces the star eternally. The other faces the void of space. This is not a gentle arrangement. The day side of WASP-103b is a vision of hell. The star, a G-type main sequence star slightly hotter and larger than our Sun, pours radiation onto the planet's surface with an intensity 1,000 times greater than Earth receives. The temperature on the day side exceeds 2,500 degrees Celsius. Hot enough to vaporize lead. Hot enough to melt iron. Hot enough that the atmosphere itself is on fire, molecules torn apart by ultraviolet radiation and reassembled in bizarre, high-temperature chemistries that do not exist anywhere in our solar system. There are no clouds on the day side of WASP-103b. There is no weather in any recognizable sense. There is only heat, a uniform, suffocating heat that permeates every layer of the atmosphere, driving convection currents that rise and fall in hypersonic chaos. Winds race from the substellar point, the single location directly beneath the star, toward the planet's limbs at speeds exceeding 5,000 kilometers per hour. These are not breezes. They are shockwaves, supersonic rivers of plasma that carry heat and momentum across the entire hemisphere. And on the night side, there is nothing. The night side of WASP-103b never sees the star. It faces outward into interstellar space, cooled by radiation into the void. The temperature drops by more than 1,000 degrees. Molecules that were ionized on the day side recombine. Gases that were superheated into plasma condense into exotic clouds of titanium oxide and vaporized silicates. It is still far too hot for liquid water, too hot for any chemistry we would recognize as life-friendly. But compared to the day side, it is almost temperate. Between the eternal day and the eternal night lies the terminator, a thin band of twilight that encircles the planet like a scar. Here, the winds from the day side collide with the cold, dense atmosphere of the night side, creating storms of unimaginable violence. Turbulence on scales larger than Earth itself. Vortices that could swallow Jupiter's great red spot. This is where heat meets cold, where motion meets stillness, where the planet's two halves wage a war that will not end until the planet itself is destroyed. And in this war, there is no equilibrium. The terminator is not stable. It shifts and writhes as the planet's deformed shape causes variations in atmospheric pressure. The tidal bulge concentrates mass at the substellar and antistellar points, creating gravitational anomalies that bend the flow of the atmosphere. Weather patterns on WASP-103b are not governed by solar heating alone. They are governed by the planet's own shape, by the stress and strain of tidal forces that pulse with every orbit. If you could stand on the surface of WASP 103b, which you cannot because the surface is likely not solid but a gradient of increasing density as you descend into the crushing abyss, you would not see a sky. You would see a furnace. The star would hang motionless overhead, an unblinking eye that never sets, never moves, never grants respite. The horizon would curve strangely, distorted by the planet's elongated shape. And you would weigh more at the substellar point than you would at the terminator, because the tidal bulge concentrates mass, increasing local gravity. This is not a place. This is a geometry of suffering. The deformation of WASP 103b is not just a curiosity. It is a window into the mathematics of planetary structure. Every planet has an interior. Earth's interior is layered: crust, mantle, outer core, inner core. Each layer has a different density, a different viscosity, a different response to pressure. When tidal forces pull on Earth, they do not deform all layers equally. The mantle, which is solid over geological timescales but flows like a viscous fluid over millions of years, resists deformation more than the liquid outer core. The result is a complex pattern of tidal deformation that can be measured with extraordinary precision using satellites and gravitational sensors. WASP 103b, however, is not Earth. It is a gas giant, a world with no solid surface, no clear boundary between atmosphere and interior. As you descend through its outer layers, the hydrogen and helium that make up the bulk of the planet gradually transition from gas to liquid to a strange quantum state called metallic hydrogen, where the pressure is so extreme that electrons are stripped from their atoms and the material conducts electricity like a metal. Metallic hydrogen has never been produced in a laboratory for more than a fraction of a second. The pressures required, hundreds of gigapascals, are beyond the reach of even our most advanced diamond anvil cells. But inside WASP 103b, metallic hydrogen is the dominant material, a churning ocean of ionized atoms thousands of kilometers deep, convecting violently as heat rises from the core and radiation pours in from the star above. This ocean is not static. It flows, circulates, responds to the tidal forces that squeeze and stretch the planet twice every orbit. The love number of WASP 103b, measured by analyzing the precise shape of its transit, tells us that this interior is not rigid. It deforms easily, like clay in the hands of a sculptor. But unlike clay, it does not hold its shape. The tidal bulge rises and falls, generating heat through friction, dissipating energy into the surrounding space. This is how WASP 103b dies. Not in a sudden explosion, not in a violent collision, but through a slow, inexorable grinding down of its orbital energy. Every time the tidal bulge rises, a tiny fraction of the planet's motion is converted into heat. Every time it falls, that heat radiates away, lost forever. The planet does not speed up. It slows down. The orbit shrinks. And the mathematics that govern this process are the same mathematics that govern the tides on Earth. The same equations that predict when the moon will rise. The same forces that have shaped our world for 4.5 billion years. The difference is scale. On Earth, tidal forces are a gentle reminder of the moon's presence. On WASP 103b, they are a countdown to annihilation. WASP 103b is not alone. It is part of a class of planets called hot Jupiters, gas giants that orbit their stars at distances closer than Mercury orbits our Sun. The first hot Jupiter, 51 Pegasi b, was discovered in 1995, and its existence was so unexpected that some astronomers initially refused to believe it. How could a giant planet, a world that should have formed in the cold outer regions of its solar system where ice and gas are abundant, end up orbiting in the scorching inner zone? The answer lies in planetary migration. Hot Jupiters do not form where we find them. They form farther out, beyond what astronomers call the snow line, the distance from a star where water ice can exist. But during the chaotic early years of a solar system, gravitational interactions with other planets, with the disk of gas and dust that surrounds the young star, can cause orbits to shift. A giant planet can be kicked inward, spiraling toward its star, sweeping through the inner solar system like a wrecking ball, ejecting smaller planets into interstellar space or consuming them entirely. When a hot Jupiter finally settles into a stable orbit, it is a survivor of violence. A refugee from the outer darkness, trapped in the inner furnace. And many of them are deformed. WASP 121b, a planet 1400 light-years from Earth, orbits so close to its star that its atmosphere is being stripped away in real time, creating a vast comet-like tail of hydrogen gas that streams behind it. The planet is so hot that heavy metals like iron and magnesium exist as vapor in the upper atmosphere. And like WASP 103b, it is deformed. Its shape is not spherical but elongated, stretched by tidal forces into an egg-like ellipsoid. HAT P7b, another hot Jupiter 2300 light-years distant, is locked in a resonance with its star's rotation, creating a complex pattern of tidal heating that drives winds across the planet at speeds comparable to the speed of sound on Earth. The planet's dayside is so hot that it rains sapphires and rubies, aluminum oxide crystals that form in the upper atmosphere and fall like snow. KLT9b, the hottest known exoplanet, orbits a star so luminous that the planet's dayside temperature exceeds 4,000 degrees Celsius. This is hotter than the surface of many red dwarf stars. The planet is not merely deformed. It is being evaporated, losing mass at a rate of 10,000 tons per second. In a few billion years, there will be nothing left but a cloud of ionized gas, a memory of a world that burned too bright. Each of these planets is a laboratory, a natural experiment in extreme physics. By studying their deformations, their atmospheric compositions, their orbital decay rates, we learn how matter behaves under conditions we can never replicate on Earth. We learn how planets die. And in learning how planets die, we learn how planets live. Because every world, including our own, is temporary. Every orbit is provisional. Every sphere is a momentary truce between gravity and chaos. The death of WASP 103b will not be sudden. There will be no explosion, no supernova-like blast that announces the end. Instead, the planet will unravel slowly, over millions of years, as the tidal forces grow stronger with each inward spiral. First, the atmosphere will begin to strip away. The outer layers of hydrogen and helium, heated to thousands of degrees and buffeted by stellar wind, will start to escape the planet's gravity. This process, called atmospheric erosion, is already happening. Observations from the Hubble Space Telescope have detected a faint halo of hydrogen around WASP 103b, a tenuous cloud of atoms that have been lifted from the planet's surface and now orbit the star independently. As the planet moves closer, the erosion accelerates. The star's radiation becomes more intense. The tidal forces grow stronger. The escape velocity at the planet's limbs drops as mass is concentrated into the tidal bulge. More and more gas streams away, forming a vast torus of material that encircles the star like a planetary wake. Eventually, the planet will cross the Roche limit. At this point, the tidal forces exceed the planet's self-gravity. The outer layers do not merely escape. They are torn away. The planet begins to disintegrate, shedding mass in great plumes that spiral inward toward the star. The process is not uniform. The tidal bulge, the regions of the planet closest to and farthest from the star, are ripped away first. The poles, which feel weaker tidal stress, remain intact longer. What is left is no longer a planet. It is a remnant. A core of rock and metal, perhaps, surrounded by a shroud of gas. This core, if it is massive enough, may survive for a time, orbiting inside the debris field of its former atmosphere. But even the core is not safe. The same tidal forces that destroyed the outer layers now work on the core. It deforms, heats, fractures, and then it too is consumed. The star grows brighter, briefly, as the infalling material releases gravitational potential energy. The debris spreads into a disk, a flat ring of gas and dust that encircles the star like the rings of Saturn but on a vastly larger scale. Over thousands of years, this disk cools, the particles colliding and sticking together, forming new structures. Perhaps small asteroids. Perhaps the seeds of new planets. Perhaps nothing at all. In the end, no trace of WASP-103b remains except a subtle anomaly in the star spectrum, a slight overabundance of heavy elements that tells any sufficiently advanced astronomer that this star once devoured a world. Computer simulations have modeled this process in exquisite detail. They begin with a healthy hot Jupiter, round and intact, and they let time run forward. The equations of gravity, fluid dynamics, and thermodynamics govern every step. The planet spirals inward, deforms, erodes, disintegrates. The simulations run for millions of years in compressed time, each frame representing centuries of slow collapse. And the simulations all agree. There is no escape. There is no last-minute reprieve. WASP-103b is already dead. It just hasn't finished dying yet. In the frozen seas of Jupiter's moon Europa, beneath kilometers of ice, there may be life. In the hydrocarbon lakes of Saturn's moon Titan, where liquid methane rains from the sky and collects in vast polar seas, there may be life. Even on Mars, in subsurface aquifers or in the deep regolith where radiation cannot reach, there may be life. But on WASP-103b, the question seems absurd. How could anything live in a place where the surface temperature exceeds the melting point of iron? Where the atmosphere is a churning plasma of ionized atoms? Where the entire planet is being slowly disassembled by tidal forces? And yet the question must be asked. Because life, as we are beginning to understand, is not fragile. It is relentless. On Earth, we have found life in places we once thought were sterile. In boiling hot springs where the water temperature exceeds 100 degrees Celsius. In the crushing pressures of the deep ocean trenches, 7 miles below the surface, where sunlight has never reached. In Antarctic ice cores drilled 2 miles down, where bacteria have survived in frozen isolation for hundreds of thousands of years. In the radioactive waste pools of nuclear reactors, where the radiation levels would kill a human in minutes. Life does not ask permission from the laws of physics. It exploits every loophole, every marginal advantage, every narrow band of temperature and chemistry where the reactions of metabolism can outrun the march of entropy. Could there be such a band on WASP-103b? The day side is too hot. The temperatures there vaporize not just water but rock. No chemical bond can survive. No structure can persist. But the night side is cooler. Not cool enough for liquid water, but cool enough, perhaps, for exotic biochemistries based on silicon or sulfur. And the terminator, the twilight zone, might be cooler still. Imagine a microorganism floating in the upper atmosphere of WASP-103b, in the thin boundary layer where the temperature drops just enough for complex molecules to form. It would not resemble any life form on Earth. Its proteins, if it had proteins, would be built from amino acids that denature at temperatures where ours would have long since unraveled. Its cell membrane, if it had a membrane, would be constructed from lipids that remain fluid at 1,000 degrees. It would feed not on sunlight, which is too intense, but on the chemical disequilibrium created by the planet's tidal heating. The constant flexing of the planet's interior drives convection, mixing chemicals from deep within the planet to the surface. This creates gradients, differences in concentration, opportunities for energy extraction, and it would reproduce fast. In an environment this hostile, longevity is a luxury no organism can afford. The winds that circle the planet could carry spores or seeds from the Terminator to the dayside, where they would be incinerated, but a tiny fraction might be carried to the night side, where they could survive, multiply, and complete the cycle. This is speculation. Pure speculation. There is no evidence that life exists on WASP 103b. There is no mechanism by which we could detect it, even if it did. The planet is 1,200 light-years away. We cannot send a probe. We cannot take a sample. We can only observe from a distance, analyzing the light that filters through the planet's atmosphere during transits, searching for the chemical signatures of biological processes. And yet the question lingers. Because if life could exist on WASP 103b, if it could cling to existence in a place this hostile, then life is not a rare accident. It is not a delicate flower that blooms only in the narrow band of conditions we call habitable. It is a weed, a tenacious, unkillable weed that will find a way to grow anywhere the laws of thermodynamics permit metabolism. And that would change everything. WASP 103b was discovered using the transit method, the same technique that has revealed thousands of exoplanets since the first confirmed detection in 1995. The principle is simple. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. By measuring the star's brightness over time, we can detect the dimming caused by the transit and infer the presence of a planet. But the devil is in the details. The dimming caused by an Earth-sized planet transiting a Sun-like star is approximately 0.008%. That is less than the flicker of a candle viewed from a mile away. To detect it requires photometric precision far beyond what ground-based telescopes can achieve. Atmospheric turbulence, light pollution, and the intrinsic variability of stars all conspire to drown out the signal. This is why we build space telescopes. The Koret satellite, launched by the French Space Agency in 2006, was the first mission specifically designed to hunt for transiting exoplanets. It operated for 6 years, staring at more than 160,000 stars, detecting 37 confirmed planets before a computer failure ended the mission in 2012. The Kepler Space Telescope, launched by NASA in 2009, took the search to another level. Kepler stared at a single patch of sky in the constellations Cygnus and Lyra, monitoring the brightness of more than 150,000 stars simultaneously for over 4 years. It discovered more than 2,700 confirmed planets and another 2,800 candidates awaiting confirmation. Kepler did not just find planets. It revealed that planets are common. That nearly every star in the galaxy has at least one world in orbit. That we live in a universe teeming with worlds. And among those worlds, Kepler found the hot Jupiters. The bloated, scorching giants that orbit so close to their stars they complete a year in days. Planets like WASP 103b. But discovering that a planet exists is not the same as understanding what it is. For that, we need more than photometry. We need spectroscopy. When light from a star passes through a planet's atmosphere during a transit, some wavelengths are absorbed by molecules in the atmosphere. By spreading the light into a spectrum and measuring which wavelengths are missing, we can determine what the atmosphere is made of. Water vapor absorbs infrared light. Carbon dioxide absorbs at specific wavelengths in the near-infrared. Methane, ammonia, sodium, potassium. Each molecule has a unique spectroscopic fingerprint. WASP 103b has been observed extensively with spectrographs on ground-based telescopes and with the Hubble Space Telescope's Wide Field Camera 3. These observations have revealed a hot, hydrogen-rich atmosphere with traces of water vapor and possibly carbon monoxide. There is no methane, which tells us the day side is too hot for methane to remain stable. There is no oxygen, which tells us there is no biological photosynthesis. The atmosphere is in chemical equilibrium, the state matter reaches when it has been heated and stirred until all reactions have run to completion. But the most important discovery came not from spectroscopy but from precise timing. By measuring the exact moment when the transit begins and ends, astronomers can infer the shape of the planet. A perfectly spherical planet produces a symmetric transit. The brightness drops smoothly as the planet moves in front of the star, remains constant while the planet is fully silhouetted, then rises smoothly as the planet moves off. But WASP 103b's transit is not symmetric. The ingress, the beginning of the transit, is slightly faster than the egress, the end. This asymmetry is the signature of deformation. The planet is elongated, and the orientation of the elongation with respect to the star changes the timing of the transit. From this timing, astronomers calculated the love number. And from the love number, they inferred the interior structure. WASP 103b is not a rigid body. It is fluid, convecting, alive with motion even as it dies. And now, with the James Webb Space Telescope, we can see more. Webb, the most powerful space telescope ever built, launched in December 2021 and began science operations in July 2022. Its infrared instruments can penetrate the glare of the host star and resolve details of the planet's atmosphere at wavelengths Hubble could not reach. Webb has observed WASP 103b multiple times, capturing full-orbit phase curves that show how the planet's temperature changes as it rotates. These observations reveal that the night side is even cooler than models predicted, that the winds do not distribute heat efficiently, that the terminator is sharper and more defined than expected. Webb can also measure the planet's deformation directly. By observing the planet at different points in its orbit, at different phases, the telescope can map the tidal bulge, revealing how the shape changes as the planet's orientation with respect to the star shifts. This is planetary science at its most fundamental. We are not just observing a world. We are watching it deform in real time. And with each observation, we refine the equations. We improve the models. We narrow the uncertainty in the planet's fate. WASP 103b is not the first deformed world we have discovered, but it is the most extreme. And its existence tells us something profound about the solar system we call home. When our sun was young, 4.5 billion years ago, it was surrounded by a disk of gas and dust, the remnants of the molecular cloud that collapsed to form the star. Within that disk, particles collided and stuck together, growing from dust grains to pebbles to boulders to planetesimals. The inner solar system, close to the sun, was too hot for ice to exist, so the planets that formed there, Mercury, Venus, Earth, and Mars, are made of rock and metal. The outer solar system, beyond the snowline, was cold enough for water, ice, and other volatiles to condense, and the planets that formed there, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants. But this tidy arrangement is not inevitable. In fact, it is rare. Computer simulations of planetary formation show that the early solar system was chaotic. Giant planets like Jupiter form quickly, within a few million years, accreting gas from the disk before the star's radiation blows it away. These giants are massive, and their gravity disturbs the orbits of everything around them. Smaller planets are scattered. Some are flung into the outer solar system. Some are ejected entirely, cast into interstellar space. Some spiral inward, migrating toward the sun under the drag of the gas disk. In most simulations, Jupiter migrates inward. It spirals toward the sun, sweeping through the inner solar system, devouring or ejecting the terrestrial planets before they can fully form. This is called the Grand Tack hypothesis, and it explains why Mars is so small. Jupiter migrated inward until it reached roughly $1.50, close enough that its gravity truncated the growth of Mars, leaving it a runt, a world that never grew large enough to hold onto a thick atmosphere or sustain plate tectonics. But then something stopped Jupiter's migration. Saturn formed, and the gravitational interaction between the two giants reversed Jupiter's course. It moved back outward, returning to the outer solar system, leaving the inner planets intact. If Saturn had formed earlier, or later, or not at all, Jupiter would have continued its inward spiral. It would have become a hot Jupiter, and Earth would never have existed. This is what WASP 103b teaches us. It is not an anomaly. It is the default. Hot Jupiters are what happens when planetary migration is not interrupted, when there is no second giant to halt the inward spiral, when chaos wins. In a universe of billions of stars, each with its own planetary system, the configurations are endless. Most systems do not look like ours. Most do not have small rocky planets orbiting in the habitable zone. Most have been rearranged by migration, by collisions, by close encounters with other stars. Hot Jupiters are common because migration is common. And if hot Jupiters are common, then deformed planets like WASP 103b are common. Worlds stretched into lemons, their deaths written in the mathematics of tidal forces. We are the exception, the lucky survivors. The planets that formed in a system where the chaos was just gentle enough, where the giants migrated just far enough and no farther, where the orbit stabilized before everything was destroyed. WASP 103b is a reminder that the universe does not owe us our existence. The search for deformed planets is accelerating. With the success of WASP 103b and others, astronomers are now actively hunting for more. They are looking not just at hot Jupiters but at smaller, rocky planets that orbit close to red dwarf stars. Red dwarfs are the most common type of star in the galaxy, making up more than 70% of all stars. They are small, cool, and long-lived. But they are also dangerous. Because red dwarfs are so dim, their habitable zones, the regions where liquid water could exist on a planet's surface, are very close to the star. A planet in the habitable zone of a red dwarf might orbit at a distance of just 5 cents, 10 times closer than Mercury orbits the Sun. At this distance, tidal forces are extreme. The planet will become tidally locked, showing one face to the star eternally, just like WASP 103b. And it will be deformed. But unlike WASP 103b, these planets are rocky. They have solid surfaces. And the question is, can a rocky planet withstand the tidal stress, or will it crack apart like an egg? The answer depends on the planet's internal structure. If the mantle is rigid, if the crust is thick and strong, the planet might survive, deformed but intact. But if the mantle is partially molten, if tidal heating drives volcanic activity across the surface, the planet could tear itself apart, becoming a lava world where the surface is constantly resurfaced by eruptions. Jupiter's moon Io is a preview of this fate. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes erupting continuously. The heat comes from tidal friction, the same mechanism that is killing WASP 103b. Jupiter's gravity stretches and compresses Io with every orbit, generating enough heat to melt the interior. The surface is a hellscape of lava lakes and sulfur plains, a world where mountains rise and fall in geological instants. But Io is a moon, small and low mass. A rocky planet in the habitable zone of a red dwarf could be far more massive, far more geologically active. It could be a supervolcanic world, its atmosphere thick with sulfur dioxide and ash, its surface glowing with the heat of continuous eruptions. And if such a world exists, we will find it. The James Webb Space Telescope and the upcoming extremely large telescopes, ground-based observatories with mirrors 30 to 40 meters in diameter will be able to detect rocky planets around nearby red dwarfs and measure their deformation. We will map their shapes. We will analyze their atmospheres. We will determine whether they are habitable or hellish. And with each discovery, we will refine our understanding of the limits of planetary survival. The line between a deformed world that endures and one that disintegrates. The mathematics of tidal death. In the long term, all orbits decay. All planets spiral toward their stars. This is not because of tidal forces alone, but because of something more subtle, more insidious. Gravitational radiation. Einstein's general relativity predicts that any mass in orbit emits gravitational waves, ripples in the fabric of space-time that carry energy away from the system. For planets orbiting at ordinary distances, the energy loss is negligible. Earth will not fall into the Sun because of gravitational radiation. The timescale for orbital decay is trillions of years, longer than the age of the universe. But for planets like WASP 103b, orbiting at extreme proximity, the gravitational radiation is measurable. Not detectable with current technology, not yet, but present nonetheless. The orbit decays not just from tidal friction but from the fundamental curvature of spacetime itself. This is the ultimate fate of all close-orbiting bodies. Binary stars, neutron stars orbiting each other, black holes spiraling together, they all lose energy to gravitational waves. And eventually, they merge. WASP 103b will not live long enough to reach that point. Tidal forces will tear it apart long before gravitational radiation becomes dominant. But the principle is the same. Every orbit is temporary. Every configuration of matter in space is provisional. The universe tends toward entropy, and entropy demands that all structure, all order, eventually dissolve into equilibrium. We live in a universe of transience. A universe where stars burn out, galaxies collide, and black holes evaporate into Hawking radiation over timescales so vast they make the age of the universe seem like a heartbeat. And yet, in this universe of decay, structure emerges. Planets form. Stars ignite. Life arises. Consciousness awakens. We stand on a rocky world orbiting a stable star, protected by a magnetic field and an atmosphere, and we look outward at WASP 103b and see our own mortality writ large across the cosmos. Because Earth, too, is dying. Not in 200 million years. Not from tidal forces. But in 5 billion years, when the Sun exhausts its hydrogen fuel and swells into a red giant, its outer layers will engulf Mercury, then Venus, then possibly Earth. The oceans will boil away. The atmosphere will be stripped into space. The surface will melt, then vaporize. What remains, if anything, will be a scorched remnant orbiting inside the Sun's outer envelope, spiraling inward through the thin plasma until it is consumed entirely. This is not speculation. This is the inevitable consequence of stellar evolution. Every Sun-like star becomes a red giant. Every planet in the inner system of such a star is doomed. The difference between us and WASP 103b is only time. But time is not nothing. Time is everything. In the 200 million years before WASP 103b is destroyed, nothing will happen on that world. No evolution. No geological change beyond the slow intensification of tidal stress. No life arising in the clouds. It is a dead world on a dead trajectory. In the 5 billion years before Earth is destroyed, everything will happen. 5 billion years ago, Earth was a molten ball of rock, still cooling from its formation. There was no life, no oceans, no atmosphere in any recognizable form. In the time between then and now, continents have formed and drifted and collided. Oceans have risen and fallen. Life has emerged from chemical soups, evolved through countless forms, conquered every environment on the planet. Intelligence has arisen. Civilizations have been built. And in the 5 billion years we have left, if we survive, we will do more. We will leave Earth. Not because we want to, but because we must. The sun is growing brighter, slowly but inexorably, as the hydrogen in its core is converted to helium. In 1 billion years, the increased luminosity will evaporate Earth's oceans. In 3 billion years, the surface will be uninhabitable. We will have no choice but to leave, to build habitats in space, to terraform other worlds, to spread across the solar system and beyond. Or we will die. This is the bargain the universe offers. Adapt or perish. Migrate or burn. The clock is ticking, and the deadline is not negotiable. WASP 103b had no such chance. It formed in the wrong place, orbited too close, and was doomed from the beginning. It is a cautionary tale, a reminder that not every world is granted the luxury of time. But we have been granted that luxury. 5 billion years. A span so vast it is almost meaningless. And the question we must ask ourselves is, what will we do with it? The lemon-shaped planet, 1,200 light-years away, will never be visited by human explorers. It is too far, too hostile, and dying too quickly. But it will be remembered. Not for what it is, but for what it represents. WASP 103b represents the universe's indifference. The cold mathematics of gravity and thermodynamics that govern the motion of worlds. The absence of mercy. The absence of justice. The universe does not care if a planet is beautiful or lifeless. It does not care if a world harbors life or if that life is intelligent. It applies the same equations to all things equally. The sphere deforms into a lemon. The orbit decays. The planet falls. The star consumes. But WASP 103b also represents our curiosity. Our refusal to accept ignorance. Our drive to look outward, to measure, to calculate, to understand. We discovered this planet not because it affects us, not because it threatens us, but because we wanted to know. Because the question, what is out there, is one we cannot stop asking. And in answering that question, we discover ourselves. We learn that our world, our solar system, our existence, is not guaranteed. That we are not the center of anything. That we are participants in a vast, chaotic, beautiful, and terrifying cosmos that does not owe us an explanation. The lemon-shaped planet is dying. But it has already given us a gift. It has shown us the limits of structure, the boundaries of stability, the price of proximity. It has shown us that the sphere, the shape we thought was inevitable, is only a temporary victory. That every world exists in a state of tension between the forces that build and the forces that destroy. And it has reminded us that we, too, are temporary. That Earth is not eternal. That the sun will not shine forever. That if we want to survive, we must become more than a single planet orbiting a single star. We must become a species that can endure the death of worlds. Because worlds will die. Stars will burn out. Galaxies will collide and tear each other apart. Black holes will evaporate. The universe itself, in the far, far future, will reach a state of maximum entropy, a cold, dark equilibrium where no structure remains, where no energy flows, where nothing happens and nothing ever will again. But that is trillions upon trillions of years from now. And between now and then, there is time. Time for life. Time for thought. Time for meaning. WASP 103b, the lemon-shaped planet, will not see that future. It will be gone in 200 million years, a cosmic eye blink. But the light from its death, the faint dimming of its star as the debris of the planet spreads into a disk, will travel outward through space at the speed of light. And in 1200 years, that light will reach Earth. And if humanity still exists, if we are still looking outward, still measuring, still asking questions, we will see it. We will see the end of a world. And we will remember that we saw its beginning, too. That we measured its shape and calculated its fate. That we understood, for a moment, the mathematics of its doom. And perhaps, in that moment, we will also understand that every world is a limb one in the universe's grip. Squeezed by forces beyond its control. Deformed by the gravity of time. The only question is, how long can we resist the squeeze before we, too, are reshaped? The universe does not answer. It only waits.